2.4 Modify Single Area OSPF version 2. And the 2.4.1, that's the Cisco OSPF cost metric. OSPF use a metric called cost to choose the best path. The main idea is very easy. The lower the cost, the better the path. OSPF calculates cost mainly based on the bandwidth of the interface. A faster interface normally has a lower cost, while a slower interface has higher cost. The formula is the cost equal to reference bandwidth divided by the interface bandwidth. By default, OSPF use 100 megabits per second as the reference bandwidth. For example, a 10 megabits per second interface has a cost of 10, while a 100 megabits per second interface has a cost of 1. There's one problem with the default setting. A 100 megabits per second interface, a gigabit interface, and even a 10 gigabits interface can all have a cost of 1. OSPF cannot tell which one is faster based on the default cost. To solve the problem, we can change the reference bandwidth using AutoCost reference bandwidth, or we can manually assign a cost to an interface using IP OSPF cost. The most important thing to remember is the higher bandwidth implies to a lower cost, which means it's better OSPF path. And when there are multiple links along a route, OSPF adds the cost together and choose the route with the lowest total cost. 2.4.2 Adjust the reference bandwidth. OSPF use cost to choose the best path. Remember, the lower cost is better, and the formula is OSPF cost equals to reference bandwidth divided by interface bandwidth. Due to this reason, all interfaces faster than fast Ethernet will have the same cost value of 1 as the fast Ethernet interfaces. We can use the command to change the reference bandwidth. So in the router configuration mode of a router, you can enter auto cost followed by reference bandwidth and then mbps command. When we change the OSPF reference bandwidth, we should configure the same value on every OSPF router. For a network with gigabit Ethernet, we can set the reference bandwidth to 1000 megabits per second. The table here shows the interface types, the reference bandwidth in BPS, and also the default bandwidth in BPS. At the end, it gives us a cost. For the first one, the 10 gigabits Ethernet, we have this number, that is 10 billion divided by 10 billion, so the cost is 1. And then for gigabit Ethernet, that's 10 billion divided by 1 billion, which is a 10. Fast Ethernet, that's 100 megabits per second. So we use the 10 billion divided by 100 million. So that's 100. The last one, Ethernet, with 100 megabits per second. So to calculate the cost, we use the 10 billion divided by 10 million. So that cost is 1000. After changing the reference bandwidth, we can check the new OSPF cost using show IP OSPF interface and then enter that interface number, such as show IP OSPF interface G0/0/0. Before changing the reference bandwidth, the gigabit Ethernet interface has a cost of 1. Then after adjusting the reference bandwidth, the cost is now 10. This will allow for scaling to 10 gigabits Ethernet interfaces in the future without having to adjust the reference bandwidth again. Here are the commands used to check and configure for reference bandwidth. First, we use show IP OSPF interface, the gigabits Ethernet 0/0/0 to check the current information about the interface. It shows the interface is up with IP address 10.1.1.5/30, area 0, and so on. And then we use config T and then enter router OSPF10. Now we are going to enter or change the reference bandwidth. Use auto cost reference bandwidth 10,000. And then the message displays reference bandwidth is changed. And then you can use the do show IP OSPF interface gigabits Ethernet 0/0/0 to confirm. As you can see, now it shows a cost of 10. 2.4.3 OSPF accumulates cost. The cost of an OSPF router is the total cost of all links along the path. In the example, the reference bandwidth is set to be 10,000 megabits per second. So the 10 gigabits link equals cost of 1. That 1 gigabits link with a cost of 10. The loopback, the cost is 1. OSPF adds the cost together from the router to the destination network. For example, from R1 to R3's loopback network, the R1 to R3 link has a cost of 10. R3 loopback, the cost is 1. So the total cost is the 10 plus 1 equals to 11. If R1 goes through R2 first, the cost for R1 to R2 is 10. From R2 to R3 is 10. The cost for R3 loopback is 1. So the total cost can be computed as the 10 plus 1 is 21. So the OSPF choose the direct path with the cost of 11. That's the lowest cost. Here we can see how the total OSPF cost appears in the routing table. R1 wants to reach R2's network, the 10.10.2.0/24. The calculation is R1 to R2 with a cost of 10. From R2 to 10.10.2.0/24, the cost is 1. So the total cost is the 10 plus 1 is 11. The show IP route command confirms this. The O 10.10.2.0/24, the 110/11 via 10.1.1.6. The important part is that 110/11. The 110, that's the administrative distance of OSPF. 11 is the OSPF metric, the total cost. The detailed output also says known via OSPF10, the distance 110, metric 11. So the router's calculation matches what we calculate manually. 2.4.4 Manually set OSPF cost value. We can manually change OSPF cost to influence which path OSPF chooses. In this example, R1 has 2 equal cost paths to reach, 10.1.1.8/30. The routing table shows O 10.1.1.8/30 with 110/20 via 10.1.1.13. That's the gigabits Ethernet 0/0/1. And then we have the 110/20 via 10.1.1.6 is for gigabits Ethernet 0/0/0. Both paths have one OSPF cost of 20. So R1 use equal cost load balancing. Path 1, that's R1 to R3, through the 10.1.1.8/30. For path 2, this is between R1 and R2 via 10.1.1.8/30. Because both paths cost 20, OSPF can send traffic over both paths. If we manually increase the cost of one interface, one path becomes more expensive. OSPF will then prefer the path with lower total cost. 2.4.7 Hello Packet Intervals. OSPF routers use hello packets to discover neighbors and make sure those neighbors are still available. By default, OSPF version 2 send hello packets to the multicast address 224.0.0.5, that is for all OSPF routers. On multi-access networks such as Ethernet and point-to-point networks, the default hello interval is 10 seconds. If an interface is configured as a passive interface, OSPF does not send hello packets from the interface. Now let's talk about the dead interval. The dead interval determines how long a router will wait without receiving a hello packet before considering its neighbor down. The Cisco's default is dead interval equals to 4 times hello interval. Therefore, the hello interval equal to 10 seconds. The dead interval is 4 times 10 seconds, which is 40 seconds. If no hello packet is received within 40 seconds, OSPF declares the neighbor down, update the LSDB, flush the change to other OSPF routers, and recalculate the best path. Let's also discuss the NBMA networks. For non-broadcast multi-access, the NBMA networks, the defaults are different. Hello equal to 30 seconds and the dead equal to 120 seconds. For this course, focus mainly on hello equal to 10 seconds. Therefore, the dead equal to 40 seconds. 2.4.8 Verify hello and dead intervals. The OSPF hello and dead intervals can be configured separately on each interface. An important rule is hello and dead intervals must match between OSPF neighbors. If the timers do not match, the routers will not form an OSPF neighbor adjacency. To check the current timer, use show IP OSPF interface command. For example, on the interface G0/0/0, the default timers are hello interval is 10 seconds and the dead interval that is 40 seconds. The show IP OSPF interface command displays detailed OSPF information for a specific interface. For R1's G0/0/0, notice these important values. The network type is point-to-point and the cost is 10. The timer interval is configured hello is 10 seconds, so the dead equal to 40 seconds. This tells us the interface is participating in OSPF area 0. The OSPF cost is 10. The network type is point-to-point. Hello packets are sent every 10 seconds. The dead interval is 40 seconds. R1 currently has one OSPF neighbor. That neighbor is router ID 2.2.2.2. The neighbor has reached full adjacency. Use the show IP OSPF neighbor command to check OSPF neighbors and their dead time. In R1, enter show IP OSPF neighbor, and you see the dead time counts down from 40 seconds. Each time R1 receives a hello packet from its neighbor, the dead time is reset back to 40 seconds. Since hello packets are normally received every 10 seconds, the timer keeps getting refreshed. In the result here, you will see 3.3.3.3, the state is full, and then the dead time still have 35 seconds left. And then for 2.2.2.2, the state is full, and then it has 31 seconds left. Both neighbors are in the full state, meaning the OSPF adjacencies are established. 2.4.9 Modify OSPF version 2 intervals. Sometimes we may want OSPF to detect a network failure faster. We can accomplish this by reducing the hello and the dead intervals. Shorter timers produce faster OSPF conversions, but they also create more OSPF traffic because hello packets are sent more frequently. Normally, the default timers are recommended and should only be changed when necessary. To manually change the timer on an interface, use following commands. First, we go to the interface configuration mode, and then use IP, OSPF, hello interval, and the seconds. This is for the hello intervals. And for the dead intervals, use IP, OSPF, dead interval, and then seconds. For example, in the interface configuration mode, for the hello interval, you can enter IP, OSPF, hello interval, and 5. And for the dead interval, you can enter IP, OSPF, dead interval, and 20. Now, hello packets are sent every 5 seconds, and the neighbor can be declared done after 20 seconds without receiving a hello. To reset the OSPF hello and the dead timer back to their default values, use no IP OSPF hello interval command, also no IP OSPF dead interval command. In this example, we change R1's hello interval from 10 seconds to 5 seconds. So in the interface configuration mode, enter IP OSPF hello interval 5. Cisco iOS automatically changed the dead intervals to 4 times the hello interval, which is 20 seconds. We can also explicitly configure it. IP config dead interval 20. However, there's a problem. If R1 use hello equal to 5 seconds, while R2 is still using hello equal to 20 seconds, their OSPF timer do not match. Eventually, the adjacency between R1 and R2 goes down. Using show IP OSPF neighbor command, we can verify that R2, the one with the router ID 2.2.2.2, is no longer an OSPF neighbor. Only R3, the 3 remains. Here we change the OSPF timers on R1's Gigabit Ethernet 000 interface. So first you enter global configuration mode for R1, and then use command interface Gigabit Ethernet 000. Now we are in the interface configuration mode. Enter IP OSPF hello interval 5, and followed by IP OSPF dead interval 20. R1 is now using hello interval equal to 5 seconds, and the dead interval equal to 20 seconds. But R2 is still using the default timers of 10 and 40 seconds. Because the OSPF timers do not match, R1 and R2 cannot remain their neighbor adjacency. after R1's dead timer expires, we see from full to down, neighbor down, the dead timer expired. Then we verify with show IP OSPF neighbor. Only R3 with router ID 3.3.3.3 appears in the neighbor table. R2, the 2.2.2.2 is gone. To restore the OSPF adjacency, we need to make the timer on R2 match R1. On R2's G0/0/0 interface, change the hello interval to 5 seconds. So the command is interface gigabit Ethernet 0/0/0, and in the interface configuration mode, enter IP OSPF hello interval 5. Once the timer match, R1 and R2 can exchange hello packets successfully again, and the OSPF adjacency quickly returns to the full state. We can verify the timers using show IP OSPF interface G000. Notice that hello is 5 seconds, the dead is 20 seconds. When we change the hello intervals to 5 seconds, Cisco iOS automatically changed the dead intervals to 4 times the hello interval, or 20 seconds. Here, we configure R2's G000 interface to use a 5-second hello interval. So the command is interface G000, and then enter IP OSPF hello interval 5. Once R2's timer matches R1, OSPF immediately begins rebuilding the adjacency. This message confirms that the process completed. From loading to